Okay, it's wonderful to have today's talk by Clayton Shonkwiler, Colorado State University, and the talk is on geometric approaches to frame theory. Clayton, to you.
Thank you. Thank you, Renzo, for the introduction. Thank you to the organizers for the invitation. Renzo and I were just chatting about how I'm a big advocate of geometry, and it's always fun to get geometry into the GEOTOP-A seminar. So this is going to be sort of geometric approaches to frame theory. So you can see a link to the slides right there, and I also posted the link in the chat if you just want to click a URL rather than typing it in. That's just if you want to see the slides or sort of go back and forth on your own. So just briefly, I want to mention that everything I'm going to say is in collaboration with Tom Needham, and then one of the things is also with Dustin Mixon and Soledad VR, and acknowledge our funding from NSF and the Simons Foundation. So here's the setup. So this is, of course, applications of geometry and topology, and the applications, so this is sort of the setup in applications. So what I'm going to say is mostly, just proving theorems in mathematics, but the inspiration comes from applications, and we are sort of interested in applications to things like signal processing and compressed sensing and data representations and things of that nature. But what I'm going to say today is mostly sort of math rather than applications. But so the setup is, one potential setup for this sort of business is you have some signal, which is a vector. Today, I'm going to be talking just about complex vectors, but you could also do this over the reals or over the quaternions, and different things apply in different settings, but we're interested in all of those cases, real or complex or quaternionic vectors. And so there's some signal. Maybe this is an image, maybe it's, some other sort of signal, and the design. So what you get to do as the designer of the system is to choose a bunch of vectors, which we call a frame, and then think of these as detectors. And so the measurements you actually get out of the system are the dot products of your chosen vectors with this unknown signal vector. And again, maybe the signal's like an image, and your frame vectors are wavelets or something like that. But in any case, this is the setup. The data you get is the dot products of some unknown vector with some chosen vectors. And then I'm usually going to represent these things as a matrix where the columns are these vectors. And then, of course, the measurement vector is just the conjugate transpose of this matrix with the signal vector. So that's what you get is F star V, basically. And then the goal is to reconstruct V from knowledge of F star V. Okay, now probably everybody immediately knows a way of solving this problem, which is like, well, just choose your vectors to be an orthonormal basis. So if I have an orthonormal basis, then any vector can be written as the dot product of that vector with a basis vector. It's a linear combination of the basis vectors and the coefficients of the dot products. So it's very easy to, given the dot products, to reconstruct the vector by just treating those as coefficients and writing down that linear combination. And written in terms of matrices, what your data was F star V, and then you just multiply that by F, and that will get you back to V. Okay, orthonormal basis solves it very nicely. What more is there to say? Well, of course, in the real world, you have to worry about things like, okay, what happens if I lose one of these measurements? So these detectors, maybe they're very cheap, and you get a lot of them, and you say, well, some fraction of them are going to go offline at any time, or maybe they're transmitting their information to me over some channel which is prone to just going offline or being too noisy to recover information from, or whatever. So what happens if I lose some of my dot products? Well, if I just have an orthonormal basis, I'm in big trouble because that means I have no way of getting back to my original vector. So this is a little bit fragile if you just use an orthonormal basis. So what you want in practice is some redundancy. So don't just take a basis, take some bigger spanning set. And the key observation, or the first key observation, is that this condition that the orthonormal basis, this sort of Parseval identity, that FF star V equals V, that can happen even when your F is not you're not just talking about an orthonormal basis. So you can have matrices that are not square, but nonetheless satisfy this condition that FF star is equal to the identity matrix. And when we have that situation, we're going to call that a Parseval frame. So in general, the idea is that N is going to be bigger than D. And so we're going to have, these N vectors in C to the D, where N is bigger than D. And the condition is that if I multiply that matrix times its conjugate transpose, I get the identity. And one sort of good way to think about this is like this FS star is just sort of the sum of the rank 1 matrices, Fi star. And for example, if the Fi's were all unit vectors, then these would all be rank 1 projectors. In general, there's sort of projection followed by a scaling. All right. So now the second key idea in this business is to be a little bit relaxed about whether you think about your matrices row-wise or column-wise. We're going to think about them sort of both ways. So the columns are these measurement vectors when we're computing dot products with. But if you think about this condition that FF star is equal to the identity, if you think about it in terms of what it's telling you about the rows, it's telling you that the rows form an orthonormal set. And so I can, if I look at the rows of this F matrix, then those rows form a frame, an orthonormal D frame in Cn. And so the space of all Parseval frames we can identify exactly with the Stiefel manifold of orthonormal D frames Cn, which is not a complex manifold, but is a real, because this condition is not a complex condition because it involves conjugation, but it's certainly a perfectly nice real manifold. It's a homogeneous space. It's a symmetric, it's a nice, Riemannian manifold. All right. So that's the space of Parseval frames. But even when we have a Parseval frame, it can still be a problem to lose measurements. So here's an example of a Parseval frame. So if I take this matrix times this conjugate transpose, I'll get the 2x2 identity matrix. But just by looking at it, you can see that this is kind of a stupid Parseval frame because the first two columns are the same. So I don't actually get any information by having the first and the second column that I didn't just have from having the first or the second. In some sense, this is good because I have redundancy. So I can, if I lose one of those measurements, I haven't really lost any information. But of course, the bad thing about this frame is that if I lose the dot product with the third column, then I'm back in this problem I had with orthonormal bases. Like I've lost information and there's no way to recover it. There's no way to get back to the signal vector that I started with if I lose the dot product with the third column, because I have no idea what the second coordinate is supposed to be. So one way of dealing with this sort of issue where I have too much information, let me say it a different way, where different columns sort of contain different fractions of the total information, is to say, okay, well, let's require all the columns to have the same norm. And you can see that would rule out this particular example of a sort of silly Parseval frame. So these are what we call equal norm Parseval frames. So it's just a Parseval frame where all of the column norms are the same. Now, if it was an orthonormal basis, of course, all these column norms could be equal to 1. They can't be equal to 1. Oh, so here's a couple of pictures. So the one on the left is a Parseval frame of 3 vectors in R2 or C2, which for obvious reasons is called the Mercedes-Benz frame. On the right, these are the vertices of a regular icosahedron, and that's a nice equal norm Parseval frame in R3. And when n is bigger than d, then these norms can't be equal to 1. It turns out that the squares of the norms have to be exactly equal to d over n. So if you want equal norm Parseval frames, then the squared norms have to be the same as the aspect ratio, sort of the d over n. People also talk about unit norm tight frames, so then you can make the vectors have norm 1, but then FF star won't actually be the identity, it will be a multiple of the identity. In fact, it'll be n over d times the identity. So you can either have FF star be the identity, or you can have the norms of the columns all be equal to 1, but you can't have both unless d equals n. But in any case, these are sort of a nice sort of generalization of orthonormal bases, and they turn out there's sort of various ways of saying, spiritually the same thing, that these frames are optimal for signal reconstruction in the presence of white noise and erasures. So I didn't mention noise, but of course there's also this issue of like, well, in practice we get noisy measurements and we want to sort of recover something that's as close as possible to the original signal. And when we have white noise, this Parseval condition is sort of optimal, and the equal norm condition ensures that even if I drop the measurement, I will still do as well as I could possibly hope to do in some least squares sense. So even more generally, we're going to think about frames where we specify the spectrum of this FF star. So again, for the Parseval frames, the spectrum would just be all 1s. But in general, maybe we don't want just to have all 1s because typically what you want to do is you want to choose this spectrum based on your noise model. So if you have white noise, you should just choose these to be all 1s or all the same at least. But if you have some other noise where the noise covariance is not a multiple of the identity but has some other spectrum, then you should choose this spectrum basically to be sort of the noise spectrum to the -1/2. But in any case, you want to choose the spectrum of this FF star matrix, or if you like, the singular values of F based on your noise model. So that's a thing that you want to sort of specify up front. And then the other thing you might want to specify up front is, well, what are the norms of the columns? And thinking in terms of detectors, these are sort of like the power of the detectors. But you can come up with situations where you say, oh, well, I particularly care about what's happening in this region, so I should let this frame vector be bigger because I want to sort of that one to have more power than the other one. So in general, you might want to specify not all the same norms, but different norms for different vectors. So this is sort of the basic parameters. You say, okay, well, I want to specify the spectrum of FF star. I want to specify the norms of the columns. And there's various natural questions to ask. The most basic one being like, well, is that even possible? Like if I choose the spectrum of FF star and I choose the norms of the columns, like, are those things even compatible? Can you form any frame that has those parameters? If there are some, like what can you say about this space? Is it smooth? Is it connected? Is it, can we sample points? Can we find, maybe even more basic thing, can we randomly sample it? Can we actually find points? Like, it's one thing to know that something is non-empty. It's another thing to actually be able to find points. So can we actually find points? Can we randomly sample it? And then, like, okay, if you had a way of randomly sampling, you would want to know, like, is a random frame expected to be sort of good or bad for whatever problem you're actually trying to solve. Okay, so I think this is a good place to sort of pause for questions if people have any. So this is sort of the setup of these are the types of objects I'm thinking about and the types of questions I'm interested in.
Yes, actually, I'm curious to understand one thing. Maybe can you when you consider noise, can you think of your data with some randomness attached to the data? So there is a kind of mean plus a stochastic value added to it. I mean, maybe in the future.
Yeah, well, so I would, the simplest sort of thing is you just say, okay, well, so here's my measurements, right? These dot products, and I say, okay, well, what I actually get is, that plus some noise, whether it's white noise or colored noise or something else. So you could think about, this vector of these measurements, plus some random vector according to whatever your noise model is. That would be sort of the simplest thing.
Okay, yeah, sure.
Okay, so I will continue, but certainly please feel free to interrupt me with any questions. All right, so so that was sort of the setup, which is sort of this problem, again, inspired by signal processing or compressed sensing, or people use these frames in CDMA, which is sort of like the second generation, wireless networking protocol and various things like that. So now here comes the geometry. So I already alluded to Stiefel manifolds, and that was some geometry. But the type of geometry I'm focused on in this case is symplectic geometry. So let me just tell you or remind you that a symplectic manifold is a smooth manifold together with a closed non-degenerate two-form. I hope to convince you in this talk that symplectic geometry has some interesting tools that if you're not sort of immersed in this world, you might not be aware of. And so maybe to encourage you to see if symplectic geometry is of interest in your life, even if you don't care about frame theory. So the sort of canonical example is the plane with the standard area form, which I will also think of as the complex plane with the form dz wedge dz bar with this I over 2 vector. And, okay, let me just remind you briefly how forms work. So a two form is going to input a pair of tangent vectors at a point and output a number, and it's supposed to do it in an alternating way. And so in this case, if I input the vectors A, B, and C, D, then what this is going to spit out is A, D minus B, C. So just the determinant of the 2x2 matrix, A, B, C, D. And notice that this is alternating, which is one of the rules. And in this case, so the rule is to be closed, non-degenerate. So non-degenerate meaning that if I plug any vector into the first slot, there's some vector I can put into the second slot to get something that's not zero. Now, in this case, it's sort of clear. Any vector I put in the first slot, if I put in any linearly independent vector in the second slot, then the area of the parallelogram will not be zero, and so this won't be zero. So it's non-degenerate. In this case, it's closed because it's a two form on a two manifold, so all two forms are closed. Here's a non-example. If I take, this essentially the same two form, but now on R3 rather than R2, well, it's not non-degenerate because if I stick the z direction in here, I always get zero no matter what the second vector is. So this sort of can't see the z direction, and so it's a degenerate two form. So that's no good. And in fact, the non-degeneracy condition is going to ensure that the manifold has to be even dimensional. If you have an odd dimensional manifold, you're always going to have sort of some direction that the two form can't see. And then another non-example is, okay, if R4 is a four manifold, okay, so that's even. Here's a two form. Which is non-degenerate, but it's not closed because if I compute the exterior derivative, I get, that y1 coefficient on the second term gives me a non-zero exterior derivative. So that's not a closed two form. And so sort of mentally in my head, I think of the closed condition as some sort of like divergence-free kind of condition. So I'll just give you sort of a laundry list of examples. So that's one we've already seen. This is actually the same one, just thought of now in slightly different way. So I can think of this two-form inputting a pair of vectors, and the output is going to be the dot product of the second vector with I times the first vector. So I think of I as sort of acting on R2 by rotation by 90 degrees counterclockwise. So if I take U, I rotate it 90 degrees counterclockwise, and I compute the dot product, then that is, in fact, the same thing as the standard area form. This is convenient to think about because if we're on what's called a Kähler manifold, that means you have both a symplectic form and a Riemannian metric, and they're related in exactly this way, that the symplectic form evaluated on a pair of vectors is the same as the Riemannian metric evaluated on I times the first with the second. So there's this compatibility. Now, once you have C, you can go to Cn by just sort of taking that standard form on each factor. And so that's, and indeed, every symplectic form on every manifold locally looks like this. It looks just like this sort of standard form on Cn. So there's no local geometry in symplectic geometry. This is, in fact, the same thing, but now if I'm thinking about m by n matrices, and I sort of write the form from the previous line in matrix language, you know, I'm saying, okay, well, so a tangent vector at a point will also be an m by n matrix, and the symplectic form evaluated here will be sort of minus the imaginary part of the trace of x1 star x2. For a compact example, the two-sphere with the standard area form, so I can think of the standard area form as, so if I have two tangent vectors u and v at a point P, I just take the vector triple product of P, u, and v, and that's a nice two form. It's certainly closed because it's a two manifold, and so this is a symplectic form. This is the same form written in cylindrical coordinates, and somehow this is a much more pleasant sort of expression. So it turns out that writing things in cylindrical coordinates on the sphere is very nice from a symplectic point of view. So the symplectic form is just d theta wedge dz. And then finally, sort of talking about physics, if you take phase space, which you can formalize as the cotangent bundle of whatever your configuration space is, in this case maybe just Rn, then I can get this sort of standard symplectic form by taking dqi wedge dpi, and here q is position and p is momentum. And more generally, every cotangent bundle has a canonical symplectic form, which is sort of constructed. I'll say more about Hamiltonian mechanics and sort of the roots of symplectic geometry in just a minute. But this is, in fact, this last example is sort of where this whole idea comes from. So, okay, what is symplectic geometry? Again, I apologize if you're a symplectic geometry expert. This is all boring to you. You know all of these things, but I'm guessing that some of you are not. You've heard these things before, but maybe haven't thought about them too much. So let me just tell you some things. What does symplectic geometry get you? So the first thing is it automatically gives you a volume form. So the non-degeneracy condition is equivalent to the statement that if I wedge this form with itself as many times as I can, then I get it. So the manifold has to be even dimensional, and so I'm going to get a top degree form, and that top degree form has to be a volume form. It's a nowhere vanishing top degree form. And what do volume forms get you? Well, I like to think about things like sampling, and so if I want to talk about sampling, I need to have a probability measure, and so if I have a volume form, I have a measure, right? The measure of a subset is just integrate this volume form over the subset. So this measure is usually called the Liouville measure, sometimes called the symplectic measure, the symplectic volume, and whenever I have a symplectic form, I automatically get this volume form and associated Liouville measure. And in particular, if my manifold is compact, then this is going to be a finite measure, and therefore I can normalize it to give me a probability measure. So whenever you're on a compact symplectic manifold, you automatically have a sort of canonical probability measure at your disposal. And that's in some sense, the reason I started thinking about symplectic geometry in these sorts of contexts to begin with. Let me just say that in some sense, this goes back to Archimedes. So I said before that the d theta wedge dz is sort of the standard area form on the unit. So there's sort of a nice picture showing, and this is what Archimedes said, right, is that the area of the cylinder is the same as the area of the sphere inscribed inside of it. And that's, if you think about it, that's really telling you that d theta wedge dz is just the standard area form of the sphere. So that's, okay. In that some sense, it's obvious that a two form on a oriented two manifold, all right. Anyway, the area form on the two sphere is certainly an area form, but all right. So symplectic geometry really comes from Hamiltonian mechanics, and I'm sort of, this is like a gross simplification, but maybe the one sentence summary is something like the evolution of a physical system follows a symplectic gradient. So what do I mean by symplectic gradient? So, okay, now I have a smooth function on a symplectic manifold, which I'm going to call H because these things are going to be Hamiltonians and they're going to be things like energy, at least in this physics context. So I have a smooth function. If I take a differential, I get a one form. Excuse me. So, okay, I have a one form, and then the fact that the symplectic form is non-degenerate guarantees that I get a sort of Riesz representation theorem that says there's some vector field which I can insert, contract into the symplectic form and get whatever one form I want. So given a function, a smooth function on a symplectic manifold, I get an associated vector field, which is usually called the Hamiltonian vector field. Sometimes I've seen it called the symplectic gradient, which is sort of morally a not terrible way of thinking about it. So if we think about the example of the two sphere, and if I take my function just to be the height function, so just, h of a point is going to give me back the z coordinate, what's the associated vector field? Well, dh, of course, is dz. And then you say, okay, well, what's the vector field I can contract into d theta wedge dz to get dz? And of course, the answer is, well, the vector field pointing in the theta direction, because that will sort of match with the d theta. So the Hamiltonian vector field associated with h, with this height function is exactly the one that sort of points along the circles of latitude. So notice that this is very much not the gradient of this function. Like the gradient would be pointing towards the North Pole. This is the gradient rotated by 90 degrees. And that's a general feature. Again, when you have a notion of multiply by I, this Hamiltonian vector field will be the usual gradient times I, sort of rotated by 90. And the thing to notice here, or one of the things to notice, is that your original function is constant on the integral curves of this Hamiltonian vector field. So again, that's very much not like the gradient. It's, instead of pointing perpendicular to the level sets, like the vector fields are tangent to the level sets of your function. All right. And so, like, this originally came, from mechanics, and so I'm just going to have a very simple system where I have a particle with mass, and it's subject to some potential. And Newton's second law, F equals ma, tells me that minus the gradient of the potential is equal to mass times the acceleration. So the second derivative of q. Okay. So now let's do this in a Hamiltonian way. So we're going to introduce momenta. So, m times the velocity. And then I can think of position momentum as living in R6, which I'm identifying with the cotangent bundle of R3. And then I get this canonical symplectic form, just dqi wedge dpi in each coordinate. Okay, so now, of course, what's the natural function in this system? Well, it's the energy function, which is going to be kinetic energy plus potential energy. So there it is. Now let's think about what's the symplectic gradient or the Hamiltonian vector field. Well, so I should compute the differential of the energy, and that gives me this thing. And then if I think about, well, what's the vector field I contract into that two form up above to get this one form? and it's exactly this thing. And okay, it's not hard to do, but you probably don't want to try to, I mean, I'm not claiming you should do this in your head on the fly, but I'll just tell you that that's what the answer is. And now if you think about, okay, what does it mean to be an integral curve of this vector field? Well, it exactly means that you satisfy this system of first order differential equations, that dqi is 1 over m times pi. Well, that's the definition of momentum, right? Pi is m times dq dt. And dp dt should be minus dv dq. So again, v was the potential and q is the position. And if you stare at this for a while, you eventually realize, wait a minute, this is Newton's second law written as a first order system. So of course, Newton's second law was a second order differential equation. If you introduce these, the first derivative variables and turn that into a system of first order differential equations, this is exactly what it is. So the moral of the story here is that, if you sort of do the Hamiltonian formulation of classical mechanics, then the system will evolve along integral curves of the Hamiltonian vector field of the energy function. And again, remember the Hamiltonian vector field, this symplectic gradient, was tangent to level sets. So energy is conserved, which of course is what it should be. So that was my statement at the beginning, that your system evolves according to the symplectic gradient. And this is really sort of the birth of symplectic geometry. Was eventually you realize, all we really needed was this two form, and you can play the same game, whether or not you can interpret your underlying space as phase space of some physical system. So this is sort of the foundations of symplectic geometry. What else do you get? I mean, this is sort of related, but so this symplectic geometry is sort of the correct setting for Newton's theorem, which again I'm going to sort of gloss as every continuous symmetry has a corresponding conserved quantity. So okay, so I have some manifold. So again, I could think of this as a state space or a phase space or a configuration space of some physical system, or I just have some abstract manifold. And when I say continuous symmetry, I really mean like, I have some action of some Lie group on this manifold. Simplest thing I could have is like an R action or a circle action. So let's just think about circle actions. So if I have a circle action on a manifold, so far I don't actually need the symplectic structure. This is true for any circle action on any manifold. I get an associated vector field, which is just sort of tangent to the group orbits. And so again, in our sort of example of the two-sphere, here's a circle action. Just rotate the two-sphere around the North Pole. And so the associated vector field is the same one we've already seen, the vector field that points along the circles of latitude. Okay, fine. So circle actions give me vector fields. Now, remember that in the symplectic setting, functions also give me vector fields. And so we're going to say that a circle action is Hamiltonian if the vector field associated to the circle action is the Hamiltonian vector field of some function. So in other words, there's some map, some function, some map to R, so that the differential of the function is the same as, okay, so I'm contracting the vector field of the circle action into the symplectic form. So in other words, the vector field generated by the circle action is the same as the Hamiltonian vector field associated with this function. All right, so this is a definition that it took me a long time to sort of internalize. So it's good to look at a simple example. So again, I have this circle action, this rotating around the two-sphere around the z-axis. So the associated vector field is this vector field pointing in the theta direction. If I contract that vector field into the symplectic form, I get dz. And we already saw that, okay, well, dz is obviously the differential of the function z. And so this circle action is a Hamiltonian circle action. and the associated map is the height function. And I should have said on here, but didn't, that this map is usually called the moment map or the momentum map. So this is a Hamiltonian circle action, and the moment map is just Z. And again, or not again, you should think of this map as recording conserved quantities of the symmetry. So if I rotate the sphere around the North Pole, I'm not changing the Z coordinates of points on the sphere. So Z is a conserved quantity of this system. And this is a way of sort of formalizing this idea that if I have a symmetry, there's an associated conserved quantity. The conserved quantity is exactly what this function gives you, this moment map. And okay, I can generalize from circles to products of circles, and in an obvious way, just each factor in the product should have this thing. So each factor gets a function. So overall, I get a vector valued function. And so if I have a symplectic manifold and a Hamiltonian torus action, so now instead of a map to R, I get a map to RK for some K. Then Atiyah and Gilman-Sternberg proved this fantastic theorem, which, I mean, this is really sort of a marvel of you know, the late 20th century mathematics. The level sets of this map are connected, and the image of the map is convex, first of all, and even better, you know exactly which convex set it is. It's the convex whole of the images of the fixed points of the group action. And then there's Doisermatt-Heckmann sort of said, okay, well, fine. Now I have if I have such a thing, well, the symplectic manifold has this Liouville measure, this associated probability, or not necessarily probability measure, but if it's compact, you can normalize it to make a probability measure. But I have this associated measure. What happens when I push that measure forward by the map? And something kind of amazing happens. The push forward measure first is absolutely continuous with respect to the Lebesgue measure. So it has a density with respect to the Lebesgue measure, and that density is continuous and piecewise polynomial, and the degree is bounded above by the difference between n and k. So here n is half the dimension of the manifold, k is the dimension of the torus. And in particular, if n equals k, then the degree is 0, and so I get a constant multiple of Lebesgue measure. So this is kind of an amazing fact that if I have a half-dimensional Hamiltonian torus action, then the push-forward measure is just Lebesgue measure, essentially, a constant multiple of Lebesgue measure. Amazing, amazing theorem. So let's go back once again to our example. So I have this, this circle action on S2. The associated moment map is just recording the z coordinate, and then again, this is basically Archimedes' theorem. Pushing forward the uniform measure on the two-sphere to the image, which is the interval from -1 to 1, which notice is convex, gives exactly 2 pi times Lebesgue measure. So this is a calculus problem that I'm sure many of us have assigned to students. What's the area of the dark gray strip of the sphere? Well, it's just 2 pi times the height difference between the bottom and the top. It doesn't matter where you are. It's only the height difference between them. So, which is kind of surprising the first time you see it. So that tells you that the push forward measure is 2 pi times Lebesgue measure on the interval. And indeed, okay, here I generated 1 million random points on the two-sphere, and I histogrammed the z coordinates, and you can see that it is in fact uniformly distributed on the interval from -1 to 1. And here's a maybe more viscerally compelling picture of that. So I'm just generating random points in the rectangle from -1 to 1 in the z direction and 0 to 2 pi in the theta direction, and then plotting the corresponding point on the two-sphere to the right. And okay, this is maybe a little bit hard to see, but you can convince yourself that those points really are sort of uniformly distributed on the sphere.
Clayton.
Yes.
Could you go back to the data display, the rectangular with the uniform? I lost I lost track. I was following you on the sphere example, and then you moved to this slide. Can you tell me what was the point?
Oh, sure. Yeah. So this is just a sort of numerical verification of this thing that I was saying. So here I'm just generating a million random points on the unit sphere. Here, this is recording the third coordinate, and here I'm just histogramming those z coordinates, and you can see that they really are uniformly distributed on the interval.
Right. Okay. Thanks.
Yep. All right. Good. So, all right. So that's my sort of interlude on why symplectic geometry is good, or some of the good things that symplectic geometry gives you. Let me now bring it back to frames. So one thing I want to say, so I defined these moment maps just for circle actions and for torus actions by just taking products. You can also define them for non-abelian groups. The definition is slightly more unpleasant. Morally, it's just saying, well, every one parameter subgroup should have this sort of circle action feature. But putting that together is a little bit weird and involves, like, your map now is not a map to R or even to RK. It's a map to the dual of the Lie algebra of the group that's doing the acting. So I'm not actually going to write down the definition, but let me just tell you, there is a definition of these sort of these moment maps for non-abelian group actions. And so with that, in our back pocket, we can then say, okay, well, what are some natural groups that act on matrices? So these frames I'm thinking of as d by n matrices with certain nice properties. What are some nice group actions on the space of d by n matrices? Well, I could multiply on the left by a unitary matrix. That's a reasonable thing to do. And the associated moment map turns out to be exactly, okay, send your d by n matrix F to the d by d matrix F times F star, which we've seen before, right? This matrix that sort of naturally showed up in frame theory. So this fact in and of itself, like, caused me to say, hey, there must be something symplectic geometry can say about frame theory, because this matrix that we really care about in frame theory is very natural from a symplectic point of view. It sort of arises as the moment map of a very natural group that acts on the space of matrices. I could also act by unitary matrix on the right, and the associated moment map turns out to be sort of the other square matrix you get by multiplying F by its conjugate transpose in the other order with a sort of spurious minus sign, which isn't so important. That matrix is usually called the Gram matrix in frame theory. It's also very important. I'm not going to talk about it so much today, but these two matrices are extremely important in frame theory, and they both come up very naturally from a symplectic point of view. Okay, what else? Well, if I wanted to think about abelian groups that act, well, I could act by diagonal unitary matrices on the left. And if I do that, the moment map turns out to record the squared norms of the rows. So my notation with the superscript indices is that those indicate the rows. So the moment map of this sort of left diagonal torus action records the squared norms of the rows. And if I act by sort of diagonal unitary matrices on the right, then that records the squared norms of the columns. And again, that's something we've seen before. We care about, okay, well, maybe we want to fix the squared norms of the columns. Well, those appear very naturally with minus signs, which aren't so important, in a symplectic setting. So notice that, okay, Parseval frames were exactly the d by n matrices, so that FF star was the identity. And so the Parseval frames are a level set of this moment map associated with the left UD action. Likewise, equal norm frames, if I want to specify, that all the norms should be the same, or more generally, I want to specify what the norms are, those correspond to level sets of this torus action. And if I want both at the same time, so if I want equal norm parsable frames, I want them to both be parsable and equal norm, then that's like an intersection of these two level sets, which maybe doesn't sound super great, but I could also think of it as the level set of the moment map associated to the product group action. So I could think of the product of the left UD action with the right torus action. And it turns out that the moment map of a product is just sort of the product of the moment maps. And so I can think of equal norm parsable frames as a level set of some product group action. And if you remember, Atiyah's theorem said that level sets are connected. And so this gives you, once you've set everything up, this gives you a sort of extremely simple proof of what we call the generalized frame homotopy theorem. So if I choose, if I think about frames with specified spectra and specified norms of the columns, then the space of those things is connected. So in other words, I can always continuously interpolate between any two frames with the same column norms and the same spectra of these FF star matrices. So this was known in the case that the FF star was the identity. So in the case of equal norm parsable frames, this was known that the space of equal norm parsable frames was connected. But this theorem tells you that there was nothing special about that. I could have chosen any spectrum of FF star. I could have chosen any norms of the frame vectors, and that space is always connected. I can always continuously interpolate between frames satisfying these sort of conditions that we're interested in. And so that's certainly of interest, but it's telling you that, like, okay, so you choose your spectrum and you choose your norms based on the whatever actual problem you're trying to solve. And this tells you no matter how you choose those things, there is a way to continuously interpolate between them, which is pretty neat. For applications like compressed sensing, it's very desirable, and you can just sort of aesthetically also imagine that this is desirable. As you say, okay, well, I have this D by N matrix. It's say equal norm parsable, or I've specified the spectrum of FF star to be something else, and I specified the norms to be something else. But in any case, I have a D by N matrix. It would sort of be nice if the columns were sort of spread out in the sense that, like, no subset should be more linearly dependent than it has to be. So one way to say that is that every D by D minor should be invertible, should have non-zero determinant. So when you have that condition, F is called full spark. And so this is ruling out situations like this. So here's a frame consisting of 4 vectors in R3, but you can see that 3 of them lie in some 2-dimensional subspace. So this is not full spark, even though it may be, if you scale things appropriately, it will turn out to be an equal norm parsable frame, but it's not full spark. And these things are sort of bad from a compressed sensing point of view, because if you are bringing in some sparse signal, if the non-zero entries happen to be associated with one of these degenerate minors, then you would not be able to actually reconstruct the signal. And the theorem we were able to prove is, I don't know, not surprising, but maybe surprisingly difficult to prove, which is, okay, again, we fixed the spectrum of FF star, we fixed the norms of the columns. There are 3 possibilities. There are 3 possibilities. So first of all, like, the space of such things could be empty. Okay, fine. That's and you can write down exactly what the conditions are. So this is an explicit condition. The second possibility is that it is impossible for a frame with these data to have full spark. So there are frames that satisfy these conditions, but it is impossible for them to be full spark. And again, you can explicitly write down exactly when this happens. The remaining possibility is that frames with these satisfying these conditions are full spark with probability 1. So any random one you choose will fail to be full spark with probability 0. So it's essentially any random one will be fine for compressed sensing purposes. So will be sufficiently robust to the data representation task. So yeah, so, and of course, to be able to prove this, we had to actually get a handle on this Liouville measure and work with that. And so the proof is very sort of symplectic geometric in flavor. But this is amazing, you know, kind of an awesome thing because it tells you basically any way you have of generating random equal Parseval frames will give you full spark ones with probability 1. Okay, so that's a sort of a nice thing to have. And I have a graduate student right now actually working on the problem of, okay, let's actually randomly sample equal Parseval frames. And this is a doable thing. It's a little bit complicated, but very much doable. Okay, so I want to close with just a few words about, well, maybe I'm not. Okay, anyway, about what's something called the frame potential. So this gets back to the early days of people thinking about equal Parseval frames. And you write down this thing called the frame potential, which in the language that I'm using is just the squared Frobenius norm of this FF star matrix. And if I think of this as a function on the space of equal norm frames, so I fix the column norms to all be what they have to be, d over n, then the minima of this function are exactly the global minima, or are exactly the equal norm Parseval frames. And so you see, okay, the equal norm Parseval frames are exactly the global minima of this function. And Benedetto and Ficus, you know, this is like 2001, proved that as a function on the equal norm frames, this function is not convex, but is sort of like a convex function in certain ways. And in particular, that then. So what the picture I've shown you is actually an energy function for, I think, d equals 2 and n equals 3 or something. So very low dimensional parameters. And you can see that there's sort of two minima, two local minima, which are global minima, but you know they're separated by a saddle point, so it's very much not a convex function. But still, like you just have to, if you land in a local min, you're done if you're trying to do some optimization, because you can't have a local min that's not a global min. You can't get trapped in sort of a spurious local min. And then what we were able to prove was to soup this up a little bit and show that if you do negative gradient flow starting from any full spark frame, and again, remember, full spark is a full measure condition. So not being full spark is a measure 0 condition. So if you start at anything that is full spark and you just do negative gradient flow, you will end up at an equal norm Parseval frame. Again, on the right, I'm showing you the actual sort of gradient vectors for this function. And you can see it is possible to get stuck on the saddle, but that's a probability 0 kind of event. For any sort of random starting point, you will eventually end up in one of these basins of attraction, which are exactly the global minima of this function. And with Needham, we also showed that the same is true for something called fusion frames, which I don't want to talk about, but are sort of a generalization of frames to another setting. And let me just, not say very much other than to say that, okay, well, this function was the squared norm of FF star. That FF star we said is a momentum map. And so this function is like the squared norm of a momentum map. And if Francis Kirwan's fantastic book on quotients, maybe the one sentence summary is like, this kind of function is awesome. And a sort of meta theorem is that if you have a reductive algebraic group action on a Kähler manifold, then the semi-stable points flow to global minima. And so this is part of sort of a broader theory called geometric invariant theory in algebraic geometry, which maybe I don't want to get into, other than just to say that, in algebraic geometry, the idea is that you think of the functions on your space. And so if you have a G action on, say, a projective variety, well, the functions are homogeneous polynomials. So the functions on the quotient should be the G invariant homogeneous polynomials. But things get a little bit dicey if you just try to you can't just take the topological quotient, for example, or you get non-Hausdorff spaces. But maybe I don't want to spend any time thinking about this. And also maybe I will skip this because I'm running out of time. And so let me just say thank you so much for listening to me, and I appreciate your attention.
Thank you very much, Clayton. Very interesting talk. Thank you. Well, I wonder if there are any question from the audience. Well, I have a curiosity, Clayton. When you talked toward the end about optimization, and then you remarked that the probability to get to a maybe you call it a spurious minimum. Well, anyway, the minimum between in the center of the saddle.
Yep.
I wonder. Well, everything you said is amazingly. It does not depend, and that's of course the beauty of it, on n. So n can be
Right.
hugely large.
Yeah. Well,
so
of course,
you
the. Sorry, go ahead.
Yeah. No, go ahead.
I was just going to say, I mean, n affects the dimension of the space that you're optimizing over, but.
Yeah, but it's amazing that you can prove that there is no risk to get trapped forever on the center of the saddle, say, and independently from n or So I guess these numbers in reality in communication technology might be very large, aren't they?
Mm-hmm.
Yeah. Okay.
Yeah,
Well,
and so this, one thing to say is like this gives you another way of just sort of coming up with lots of examples of these things. You just like take any d-billion matrix and follow this gradient flow, and you will limit to one of these equinole parallel frames. So that's kind of a nice upshot is that it's in some sense easy to construct these things.
Right. Well, I was also interested to see how much you drew from symplectic mechanics, and maybe a topic that is related to an area then becomes interesting, useful, and available to other areas of exploration. Questions?
Yeah, for sure.
May I ask a question?
Okay. If none, thank you very much, Clayton. Thank you. Yes?
Hold on, I think Irina had a
go
question.
on.
It just the theorem which you
Yes.
showed about that either you don't have frames or you plenty of them with probability 1 of spark. Is there any specific condition? Could you say is there any specific condition on spectrum and length which you would say, okay, check this and you will know in which of the 3 scenarios you are?
Yeah, so the conditions are completely explicit. So basically, it's an issue of you have a system of inequalities involving the spectrums and the lengths. So it's basically majorization, and so you have the spectrum has to, let's see, which way does it go? The spectrum has to majorize the length, the squares of the norms. And that means that if I take sort of the sum of the squares of the norms of the FIs for I going from 1 to k, then that should be less than or equal to the sum of the first k eigenvectors of FF star. And if you ever, so that's like a system of inequalities. And if you ever get equality in any of those, then you're in sort of the bad case where you can't have full spark. Otherwise, if all of those inequalities are strict, then you're in the third case where everything is full spark. And if you fail to satisfy any of those inequalities, you're in the first case where there's nothing. So it's very explicit in terms of inequalities.
Thank you. And fantastic talk. I really enjoyed it, and I'm grateful that I came.
Great. Thank you so much.
Thanks.
Okay, if no other questions, thank you again, Clayton. Thank you very much.